Hello, this example is on power and the Poynting vector. So in free space, for example, given this magnetic field intensity capital H, and notice that H varies with x, so it's traveling in the x direction, but it's pointing in the z direction in amps per meter. Find the total power passing through, and then we've got part A, which is a square plate located on some plane, and part B is a circular plate or disk located on a different plane. All right, now given that we're dealing with power and all of our results for power relate to the electric field, we're first going to find the electric field, not the because we're given the magnetic field. So let's recall that E0 was eta 0 because we're dealing with free space here. So this is the intrinsic impedance of free space times H0. And if you recall, the intrinsic impedance of free space is a purely real number, so it does not change the phase of H. So that means that the electric field and the magnetic field are in phase with one another. So this implies then, being that eta 0 is purely real, we can just say that the electric field is 0.2, which is the amplitude of the magnetic field, times eta 0 times the cosine of omega t minus beta z. Okay, we have to talk about not beta z, excuse me, beta x. We have to talk about the direction of the electric field. But so basically what we've done here is we've just taken eta 0 times h0, but we need to change the direction. So we need to think of what is the direction of the electric field, and let's recall that when I take the electric field, or a unit vector in the direction of the electric field, cross it with a unit vector in the direction of the magnetic field, I should get a unit vector in the direction of propagation. So we're not sure about this guy, but H is in the z direction, right? And the direction of propagation is along the x direction. So what does the direction of E have to be here? And I'll let you think about that. It's probably either y or minus y, right? So let's try y. So point your fingers of your right hand in the direction of y, curl them towards the direction of z, and does your thumb point in the direction of x? Yes. So pause the video if you want to do that slower, but this needs to be y, not minus y. So we're going to say a y there, and this is in volts per meter. Okay, so that's our electric field, and we know what the average power is, kind of with this script P sub av. That is this E0 squared divided by 2 times the magnitude of eta, right? We found this equation previously in a previous video, times e to the minus 2 alpha x, because it's propagating in the x direction, cosine of the angle of the intrinsic impedance eta, and then this would be the power is in the direction of the propagation, so this would be ax in this case. Now, for our specific case, we've got E0, which we just found, and 2 times, and then the magnitude of eta. Well, we said eta is a real number, and so and it's positive, of course. So this just becomes eta 0, and then because it's a real number, its angle is 0. It introduces no phase shift between the electric and magnetic field. So cosine of 0 is 1, and we've got alpha is also 0. Alpha is 0 because this is in free space, so this thing is not decaying at all. The amplitude is not decaying, and so we arrive at this here. The average power is E0 squared over 2 times eta 0 in the x direction. So what does that mean then for the total power? So now we will look at part A. So this what we got here, the script P, this is per unit area. So now this vector is traveling through this square plate, Okay, and so this square plate has a certain area, so now we need to do some sort of integration over this plate. And so we have now P average, not script. Okay, actually let's back up. How can we get a normal vector to this plate is the question, because we're going to have to do a dot product with the surface area. So remember, we've used this trick many times now. We can write that plane x plus y. If I subtract the 1 over to the other side, I have x, y, 1 dotted with 1, 1 minus 1 equals 0. So that's the trick that we've always been using. And so the normal vector, here's what we look to find the normal vector. A vector that is normal to this plane is 1 over root 2 times ax plus ay. Again, we've been using this trick for quite some time now, going back to our study of vector calculus back earlier in the course. Okay, so that's our normal vector, and so that means that our differential surface vector, surface area vector, is dx dy, right, because x and y we've got components of, over the square root of 2, right, because of this guy, times ax plus ay. That's our differential surface area vector. Okay, so now we are ready to do the integration. So I've got P without the script, av, equals, so this is in watts now. We're going to integrate over our surface of E0 squared 2 times eta 0 in the x direction, right? That's the script P. This is watts per unit area. Then we're going to dot that with our surface vector, our differential surface vector, that is, dx dy over the square root of 2 ax plus ay, like this. And so remember that the way the dot product works, ax dotted with ay is 0 because they're orthogonal. Ax dotted with ax is 1, so I pick up that guy there, only the x component. So this is E0 squared is a constant. I can bring that out. I've got 2 times a root 2. I can bring that out. And I've got an eta 0 there. I can bring that out. Those are all constants. Then I've got an integral over the surface dx dy. Okay, so dx dy over the surface, and then that's just the area of this thing. So this becomes E0 squared 2 root 2 eta 0 times the area of this thing, but I need to put it in square meters. So this is 10 times 10 to the minus 2 squared, right? Each side is 10 times 10 to the minus 2 meters. Square it, that gives me the area, and so I punch all this in. Oh no, I need to pick up the surface area. Oh no, excuse me. This is the surface area here. E0 we were saying is this thing here. So actually, before I punch everything in, let me make sure I know what I'm punching in. E0 is the amplitude, so this is 0.2 squared, and then eta 0 squared. Okay, and then I've got the 10 times 10 to the minus 2 squared divided by 2 root 2 eta 0. So you'll see that one of the eta zeros cancels. Okay, so what is eta 0? If you remember, eta 0 was 120 pi approximately. So you can plug that in and you should get 53.3 milliwatts of power. Okay, that's our answer for part A. Okay, so B is very similar, but we have a different plane and a different area. So notice this thing is on the plane x equals 1, so that means that a normal vector to that plane is simply an equals ax. That's nice. So then our differential surface area vector, ds, is just dy dz, right? dy and dz are changing, times ax, like that. Okay, so again, I put ds in, and I do the dot product of script p with ds, and that picks up only the x component of this thing. So now I've got my p, which is not scripted. Again, I can pull out e0 squared over 2 eta 0, right? And now I've got over the surface dx dy. Okay, so again, I'm just using the results from the previous calculation. So this all stays the same. That was due to our electric field, which is not changing from parts A to B. The only thing that's changing is the surface, which is this thing. So this was ds. Okay, but now I'm saying that ds is this thing here. Okay, so again, I've got just a constant times dx dy, so when or that should be dy dz, excuse me. I think I gotta change my notes on that. It should be dy dz. dy dz. Okay, so when I integrate a constant times dy dz over the surface area, all I get is the surface area. So this is e0 squared times the surface area divided by 2 eta 0. And then I can again do the cancellation with the eta. So this is 0.2 squared, then there's just 1 eta 0 there. And then there's a pi times the radius squared, right? Pi r squared for the area divided by 2. And so I punch those numbers in and I get 59.2 milliwatts. Like that.